Welcome to the fascinating world of Google Maps, where advanced mathematics meets real-world navigation. Have you ever wondered how your phone calculates the fastest route in seconds? Behind the scenes, Google Maps uses a powerful mathematical structure called a graph. This video will take you through the core concepts, showing how graph theory transforms the physical world into a digital map, enabling efficient pathfinding and real-time rerouting. Let's start by understanding how Google Maps abstracts our roads and intersections into nodes and edges, setting the stage for lightning-fast navigation. Its core, Google Maps represents the world as a graph, denoted as G equals VE. In this structure, every location where a decision can be made, like intersections, dead ends, or bends, is a vertex or node. The roads, highways, and paths connecting these points are called edges. By mapping the physical geography into these graph components, Google Maps can run complex algorithms to find the most efficient route between any 2 points. This abstraction is the foundation for all computational pathfinding in the app. Vertices, also known as nodes, are the backbone of Google Maps' graph. Every intersection, dead end, or curve on a highway is represented as a vertex. These are the points where you can make decisions, turn left, go straight, or take a detour. By breaking down the map into these decision points, Google Maps ensures that every possible route is accounted for. This granular mapping allows for precise navigation, even in complex city layouts or winding country roads. Edges in the graph represent the roads, highways, and walkways that connect the vertices. Each edge is a possible path you can travel, linking one decision point to another. Google Maps carefully models these connections to reflect real-world conditions, including one-way streets and two-way roads. By representing every possible route as an edge, the app can calculate the best way to get from point A to point B, considering all available options. Real-world roads aren't always bidirectional. Google Maps uses directed edges to model one-way streets, ensuring that navigation respects traffic rules. For two-way streets, the app creates two separate directed edges, each pointing in opposite directions. This approach allows the algorithms to accurately reflect the flow of traffic, preventing navigation errors and keeping users safe. Directed edges are a crucial detail in making digital maps match real-world driving conditions. Google Maps isn't just for drivers. The app supports walking, cycling, and public transit, each with its own set of edges. Multimodal edges ensure that pedestrian walkways, bike paths, and highways are only accessible in the appropriate mode. For example, a pedestrian path is an edge in the walking graph but not in the driving graph. This flexibility allows Google Maps to provide tailored routes for every user, whether they're on foot, bike, or car. Not all edges are equal. Each edge in Google Maps is assigned a weight representing the cost of traveling that path. These weights can be based on physical length, speed limits, traffic lights, or toll booths. The goal is to minimize the cumulative weight, ensuring the fastest or most efficient route. By assigning weights, Google Maps can prioritize routes that are quicker, safer, or more convenient for the user. Google Maps takes edge weights to the next level by adjusting them in real time. Using crowdsourced speed data, accident reports, and construction updates, the app constantly recalculates the weight of each edge. This means your route adapts to current conditions, avoiding delays and detours. The weight of an edge now represents estimated travel time, not just physical distance, making navigation smarter and more responsive. Weight of an edge is calculated using a formula that combines distance, delay costs, and real-time speed. This approach ensures that the Pathfinder selects routes based on actual travel time, not just the shortest physical path. By factoring in delays and current speeds, Google Maps delivers routes that are optimized for the present moment, helping users avoid traffic jams and unexpected slowdowns. Find the best route. Google Maps relies on advanced pathfinding algorithms. Classical methods like Dijkstra's and A are the foundation, but Google uses highly optimized variants to handle the massive scale of global navigation. These algorithms explore the graph, calculating the lowest weight path between any 2 points. Let's dive into how each algorithm works and why they're so effective for real-time navigation. Invented in 1956, Dijkstra's algorithm finds the shortest path from a starting node to all other nodes in a weighted graph. It works by iteratively exploring neighboring nodes with the lowest cumulative edge weight, using a priority queue. This method is efficient for smaller graphs and forms the basis for many navigation systems. Google Maps adapts Dijkstra's algorithm to handle vast networks, ensuring quick and accurate route calculation. The time complexity of Dijkstra's algorithm is O, V plus E log V when using a binary heap. This efficiency allows Google Maps to process millions of routes quickly. By optimizing the underlying data structures, the app can scale up to global navigation, providing real-time results even in dense urban environments. While Dijkstra's algorithm explores all directions equally, a asterisk search uses a heuristic function to estimate the distance from the current node to the destination. This allows the algorithm to prioritize nodes that lie in the general direction of the goal, making it more efficient for long-distance navigation. Evaluates nodes based on the sum of actual cost and heuristic cost, focusing on routes that are likely to be optimal. Heuristic function in A is typically the straight-line distance, also known as the crow flies metric. By estimating how far a node is from the destination, the algorithm can focus its search on the most promising paths. This approach reduces unnecessary exploration, speeding up route calculations and improving efficiency, especially for cross-city or cross-country navigation. Evaluates each node using the formula Fn equals Gn plus Hn, where Gn is the actual cost from the start to the node and Hn is the heuristic cost to the destination. This combined score helps the algorithm prioritize nodes that are both close to the start and likely to lead to the goal. The result is faster, more targeted pathfinding, ideal for real-time navigation in Google Maps. For global navigation, running Dijkstra or A on billions of nodes is too slow. Google Maps uses contraction hierarchies to pre-compute shortcuts on major highways. The algorithm contracts minor local streets, leaving a sparse network of arterial roads and highways. This optimization allows the app to quickly route users across long distances, switching between local and highway graphs as needed. In calculating a long-distance route, Google Maps first routes you from your local street to the nearest major highway using the local graph. Then, it travels across the pre-computed highway shortcut network before routing you back down to the destination's local streets. This layered approach ensures fast and efficient navigation, even across vast regions. One of Google Maps' most impressive features is dynamic rerouting. If traffic slows down on a specific edge, the weight of that edge increases in real time. The engine instantly recalculates the lowest weight path, detouring you to a faster route. This capability keeps users moving efficiently, even when unexpected delays occur, making navigation adaptive and reliable. Google Maps leverages crowdsourced traffic data from millions of users. By collecting speed and location information, the app can detect traffic jams, accidents, and construction zones. This data feeds into the dynamic weighting system, ensuring that routes are updated in real time. The result is a navigation experience that adapts to current conditions, keeping users informed and on the move. In addition to real-time data, Google Maps uses historical trends to predict traffic patterns. By analyzing past speed data, the app can anticipate rush hours, weekend slowdowns, and seasonal variations. This predictive capability helps users plan ahead, choosing routes that are likely to be clear based on historical insights. Google Maps integrates accident and construction alerts into its routing engine. When an incident occurs, the app increases the weight of affected edges, steering users away from delays. This integration ensures that navigation remains efficient, even when unexpected obstacles arise, keeping users safe and informed. Speed limits are a key factor in edge weighting. Google Maps incorporates speed limit data to estimate travel times accurately. By considering legal speed restrictions, the app ensures that routes are both safe and efficient, helping users avoid speeding and arrive on time. Traffic lights and toll booths add delay costs to certain edges. Google Maps models these features to provide realistic travel time estimates. By factoring in stops and tolls, the app helps users choose routes that minimize delays and expenses, optimizing both speed and cost. Google Maps offers specialized routing for pedestrians and cyclists. By activating different edges in the graph, the app provides routes that are safe and accessible for walking or biking. This multimodal capability ensures that every user gets a tailored navigation experience, whether they're on foot, bike, or car. For public transit users, Google Maps activates edges representing bus routes, train lines, and subway tracks. By integrating transit schedules and stops, the app provides efficient routes for commuters. This mode-specific routing ensures that users can navigate complex transit networks with ease. The core goal of Google Maps is to calculate the shortest or fastest path between 2 points. By combining edge weights, real-time data, and optimized algorithms, the app delivers routes that minimize travel time and distance. This capability is the heart of digital navigation, guiding millions of users every day. Pathfinding algorithms like Dijkstra's use a priority queue to manage which nodes to explore next. By always selecting the node with the lowest cumulative weight, the algorithm ensures efficient exploration. Google Maps optimizes this process to handle massive graphs, delivering quick results for users worldwide. Using a binary heap for the priority queue improves the efficiency of pathfinding algorithms. This data structure allows for fast insertion and extraction, speeding up route calculations. Google Maps leverages these optimizations to scale up navigation, ensuring real-time performance even in large cities. Navigating the entire world presents unique challenges. Google Maps must handle billions of nodes and edges, requiring advanced algorithms and data structures. By pre-computing shortcuts and optimizing local graphs, the app delivers fast, accurate routes across continents, cities, and neighborhoods. To speed up long-distance navigation, Google Maps pre-computes shortcuts on major highways. These shortcuts reduce the number of nodes the algorithm needs to explore, enabling quick route calculations. By focusing on arterial roads, the app ensures efficient navigation across large regions. Minor local streets are contracted in the graph, simplifying the network and reducing computational load. This process leaves behind a sparse network of major roads, making pathfinding faster and more efficient. Google Maps seamlessly transitions between contracted and detailed graphs as users move from local to global routes. Google Maps uses a layered routing approach, combining local and highway graphs. This method allows the app to quickly route users from their starting point to a major road, then across the highway network, and finally down to the destination's local streets. The result is fast, reliable navigation for both short and long journeys. When conditions change, Google Maps instantly recalculates the best route. If the weight of your current path increases due to traffic or delays, the app triggers a recalculation step. This ensures that users are always on the fastest available route, adapting to real-time changes seamlessly. If an alternative path becomes faster due to changing conditions, Google Maps switches routes automatically. The app compares the weights of all possible paths, selecting the one with the lowest cumulative cost. This dynamic selection keeps users moving efficiently, even when unexpected delays occur. By combining graph theory, real-time data, and optimized algorithms, Google Maps delivers a seamless user experience. Navigation is fast, accurate, and adaptive, helping users reach their destinations efficiently. The app's intelligent routing keeps travel stress-free, even in complex or changing environments. Safety is a top priority for Google Maps. By modeling one-way streets, speed limits, and real-time incidents, the app ensures that routes are safe and reliable. Users can trust the navigation to guide them through unfamiliar areas, avoiding hazards and delays. Urban environments present unique challenges, with dense networks of roads and frequent changes in traffic conditions. Google Maps uses graph theory to efficiently navigate cities, adapting routes in real time and minimizing delays. This capability is essential for commuters and travelers in busy metropolitan areas. In rural areas and on highways, Google Maps leverages contraction hierarchies and pre-computed shortcuts to deliver fast navigation. By focusing on major roads, the app reduces computational load and ensures efficient routing across long distances. This approach keeps travelers moving smoothly, even in remote regions. Google Maps integrates with other services such as ride-sharing and delivery apps. By sharing routing data and traffic information, these services can optimize their operations, providing faster and more reliable experiences for users. This integration expands the impact of graph theory beyond navigation. Google Maps is constantly improving its algorithms and data sources. By incorporating new technologies and user feedback, the app refines its routing engine, delivering better navigation every day. This commitment to innovation ensures that users always have access to the latest advancements in digital mapping. Graph theory isn't just for mathematicians, it's a part of everyday life through Google Maps. By abstracting the world into nodes and edges, the app makes complex navigation simple and accessible. Whether you're commuting, traveling, or exploring, graph theory guides your journey, making technology work for you. The future of navigation lies in even more advanced graph theory and real-time data integration. As technology evolves, Google Maps will continue to innovate, providing smarter, faster, and safer routes. The possibilities are endless, with new modes of transport and smarter algorithms on the horizon. Summarize: Google Maps uses graph theory to model the physical world, assigning weights to edges and employing advanced algorithms for pathfinding. Real-time data and dynamic rerouting ensure efficient navigation, while multimodal edges provide tailored routes for every user. This combination of mathematics and technology powers one of the world's most popular navigation tools. Google Maps has revolutionized daily travel, making navigation faster, safer, and more reliable. By leveraging graph theory, real-time data, and optimized algorithms, the app helps millions of users reach their destinations with ease. The impact is felt in cities, suburbs, and rural areas alike, shaping the way we move through the world. In conclusion, Google Maps is a testament to the power of graph theory and modern algorithms. By abstracting the world into nodes and edges, assigning dynamic weights, and employing efficient pathfinding, the app delivers unparalleled navigation. As technology advances, Google Maps will continue to lead the way, making travel smarter and more connected for everyone.